And I'm back this time with the Chapter 9 applications video. So let's apply some of those concepts that we talked about in the linear momentum and collisions concept video. We are going to start with a problem that involves 3 different birds. So we have 2 ducks and a goose. And I've given you the image to help you visualize this. So we see duck number 1 here is heading in the x direction. So we've drawn our coordinate system to make the most sense. It's like this. There's x and here's y. And then we have duck 2 who's coming in this direction, and we have the goose who's moving upward towards the origin. I've given you some information about the velocities, and I want you to find the magnitude and the direction of the total momentum of the 3 birds. Okay. We obviously have stuff happening in both the x and the y directions right now, so we're going to have to factor that in. Let's start with duck 1, and we're going to go ahead and calculate the momentum for duck 1. Well, that would be P of, I'm going to say duck 1 equals mv. Now, when we look at this first duck, we see it's only moving in the positive x direction. So we don't even need to write anything for y because nothing's happening in the y direction for that duck. So I can just plug in my information and I see that the duck is 4 kilograms. I was told that up here. And its velocity is 1.10 oops, that should say meters per second. Let's do the same thing for the second duck. So the second one, okay, it's mv. For duck 2, we see that it only has movement in the y direction, and it's moving down, so this actually has movement in the negative y direction. And I'll indicate that over here. This is only the x direction, and this one is only the y direction. Again, since it is moving in the negative y direction, we have to put a negative out here. It's 4 kilograms, and its speed is also 1.10 meters per second. That's only in the y direction. And finally, let's do this for the goose. The goose is traveling only in the y direction, the positive y direction, so we don't need a negative. And its mass is 9 kilograms, and its velocity is 1.30 meters per second. Again, only in the y direction. So we can do the math on each of these and find the momentum. So the first one, that one is going to be equal to 4.40 kilogram meters per second. This second one is the same but opposite, negative 4.40 kilogram meters per second. And finally, the momentum of the goose is 11.7 kilogram meters per second. And sorry, this is in the y direction, this is in the y direction, and this is only in the x direction. I'm going to leave those so I can make sure we don't make a mistake later. So I have found the momentum of each individual duck, and I've indicated the direction. Now we want to find the total momentum of all of those birds together. So I'm going to have to add everything up. So my total momentum is just the momentum of the first duck plus the second duck plus the goose. But notice, because of these x and y components, that we can't simply add all of our numbers together, all of our values together. We're going to have 4.40, and that's in the x hat direction, plus a negative 4.40, but that's in the y direction. And then we have an 11.7, which is also in the y direction. So the total momentum here, P total, will be 4.40 in the x hat direction plus 7.30 in the y direction. So I have that piece of information. I know that my total is going to be equal to this. But what exactly is the total? We want to find the magnitude of our total momentum. To do that, we are going to use the following equation. And I think I'm going to have to go back and erase because this is not going to work. The total momentum in the x direction squared plus the total momentum in the y direction squared. And that is going to let us solve for P total. I am going to have to go back and erase. I'm running out of room up here. Okay, this got me a little bit of room, so I'm going to work with that. All right, so we have 4.40, and that's squared plus 7.30 squared, and we need to find the square root of that in order to solve for P total. Once we do this math, you're going to find that our P total is equal to 8.52 kilogram meters per second. Okay. And finally, for the direction of the total momentum, so it's going to be a combination, and it's going to have an x and y component, so we see what that vector looks like here. We need to use a formula that we've worked with a lot in the past. Okay, so this is a triangle. We can treat it like a triangle, like this. Oh, we're not using the pen right now. Like a triangle. Okay, so we are actually going to use the tangent because we have each of these sides of our triangle. We have the x and the y values. And to do that, we know our tangent of theta is, remember SOHCAHTOA, okay, it's opposite over adjacent. That's what tangent is, opposite, which is the y direction over adjacent, like this. And I'm sorry, that's the momentum in each direction. To find theta, I'm going to have to take the inverse of this. So when I plug in those values, I should find that my final direction is equal to 58.9 degrees. Okay, and that is it for problem number 1. Okay, problem number 2. This time we are looking at another baseball problem. And we see that it is moving toward home plate. Okay, and I'll sketch this out. So here is our batter. And here is the pitcher. And we know the ball is moving towards home plate. Okay, so generally we would want to set our X direction to be like this. Okay, because the batter would be hitting the ball out into the field. But in this case, we see that the ball is moving towards home plate with this speed. The batter then hits the ball softly, exerting this force over this amount of time. If the average force is directed towards the pitcher, which is what we're going to take to be the positive x direction, okay, so it even told us here which direction to make this, what is the final speed of the ball? So we know the mass, we know the initial velocity of that ball, we know the force, and we know the time. I hope that you immediately noticed that this time was given to you in milliseconds, and we're going to need to convert that to seconds, which would be 0.00130 seconds. So if you take a look at that equation sheet, Let's see what we could possibly use. Well, we know the force over a certain period of time. That's the same thing as the impulse. So I equals that force times delta t. That is also equal to the change in momentum, and that's what that momentum impulse theorem tells us. So that means I is just equal to P final minus P initial. Well, we can rearrange this to just tell us the value for P final, which would be I plus initial momentum. And if we recall, momentum is just mass times volume. Okay, not volume, velocity. I keep calling V volume, is mass times velocity. And we have both of the pieces of information for the initial mass and velocity. Since we have that, we'll be able to plug some of this information in, and then later we can solve for that final velocity. So let's go ahead and solve for PI. Okay, it's mass times initial velocity. We know that's 0.144, and this is 43.0 meters per second. So our initial momentum is equal to negative, oh, I'm sorry, I definitely left this out up here. I keep doing that with these negatives. I'll add it back in. And this is in the X, oh no, this is in the X direction. Okay, since initially it says the ball is headed towards home plate, so towards home plate, that means the ball is initially headed this way. That's the negative X direction, so we need to put a negative here. Okay, so we have our initial momentum. We've also been given all the information we need to find the impulse, because we just need the force multiplied by the time. So let's go ahead and find that as well. That would be 6.50 times 10 to the third newtons. Okay, and we're going to multiply that. Oh no, I don't have room. Okay. Times 0.00130 seconds. So we're going to find that the impulse is equal to 8.45 kilogram meters per second, and this is also in the X direction. Oh, per second squared? Oh no, per second. Yes, that's correct. Thought I made another mistake. Now let's go ahead and substitute in all of the information that we know. So we have I and we have the initial momentum, which means we can easily solve for the final momentum. Okay, so initially we have 8.41, and that's kilogram meters per second, plus, I got a negative, 6.19 kilogram meters per second. Okay, our units are the same, so we can just add them together to get 2.26 kilogram meters per second, and that is in the X direction. So to solve for speed, we know the final momentum is equal to the mass times the velocity, the final velocity. Rearrange, we know final velocity is equal to final momentum divided by m. Plug that information in, and it's 2.26 divided by 0.144, and that gives us 15.7 meters per second, and that is in the X direction. Okay, so that is how you would use the initial velocity, the mass, the force, and our time to solve for the final velocity. Moving right along, let's try another problem. And yes, there are a lot of words here, so please do not get overwhelmed. In fact, why don't you pause this and take a moment to read this so that I do not have to read it to you. Okay, so let's go ahead and start working this problem. We were given information for the mass. And we were told the impulse under this first part of the curve. So the impulse from 0 to 0.3 seconds. And then we were told a second impulse that occurred from 0.3 to 0.8 seconds. So that's going to be important information. So this is I2, and this part is associated with the first impulse. We have been given quite a bit of information in this problem, so it's actually going to be more straightforward than you would think. They told us what the impulse is for part 1 and for part 2. So to figure out the total impulse so that we can go on to calculate the horizontal force, the average force, we'll just say I1 plus I2. All right, this is easy so far. That's negative 2.7 plus 26.2. And that comes to 23.5 kilogram meters per second. To find the average force, let's just use the fact that I is equal to force multiplied by the change in time. So we can find our average force because we know the total time. The total time is 0 to 0.8 seconds. So we can find that average force. Okay, so 23.5 equals the average force multiplied by 0.8 seconds. So our average force ends up being about 29 newtons. Okay, so this is the answer for part 1. Now for part 2, we're trying to find the jogger's change in speed. So pause this video and try that and then press play when you're ready. Okay, I hope this part went well too. So for the second part, let's go ahead and use I equals force multiplied by the change in time, which is the same as the change in our momentum. Well, the change in momentum is the same as mass times a change in velocity. So we can go ahead and say that I is equal to a mass times the change in velocity. Well, let's just rearrange. We get the change in velocity. Oh, what am I doing? I need to solve for that. The change in velocity is equal to our impulse divided by our mass. Plug in our numbers. We get 23.5 divided by 71 kilograms. We should find our change in speed is 0.33 meters per second. So even though this was very wordy and it involved a graph, this problem was actually not that bad to work. Okay, so we will be looking this time at, and I'll kind of draw this one. It says we have a lumberjack who's standing on a log. So here is my log. Here is my man standing on top of the log. There he is. Got an axe in his hand. He's a lumberjack. That does not look like an axe. I don't know what that looks like. And it says we are going to take the positive direction to be towards the shore. So here's our shoreline. So this is my positive x direction. We want to know what happens if the lumberjack starts walking along the log towards the shore, so in the positive x direction with some speed, and the log moves away from the shore. What is the speed of that log relative to the shore? Is it going to be greater than, less than, or equal to the velocity that the lumberjack is walking with? Okay, so we don't have numbers in this problem. And I want you to take a moment to think about the velocity and whether or not it will be greater than, less than, or equal to the velocity of the lumberjacks, or of the walking speed of the lumberjack. So take a moment and think about that. Okay. Now, before the man is walking, before this lumberjack is walking, he has no velocity. Okay, before he's walking, he has a velocity of 0. The log also has a velocity of 0 beforehand, so neither of them are moving. And it even says that both the log and the lumberjack are at rest initially. That means there is no momentum initially, because if velocity is equal to 0, then momentum is going to go to 0 as well. That means that the speed of the log relative to the shore is less than the velocity of the lumberjack as he was walking. Okay, now why? The momentum of the lumberjack is balanced out by the momentum of the log. So, since the mass of the log is a lot greater than the mass of the man, we know that the speed of that log will actually be less than the velocity. And I hope that makes sense. Okay, so that's your explanation. The answer and the explanation is going to be less than velocity, and I told you why. It's because the log is more massive than the lumberjack. And since the momentums were originally balanced out, the mass of that log being greater is going to result in a velocity that's lower than the lumberjack's walking speed. Part B. If the lumberjack is walking with a velocity of 1.8 meters per second relative to the shore, we want to know the velocity of the log relative to the shore. We're going to ignore the friction that exists between the log and the water. Okay, in this part, if you don't care to think about the concepts, you might enjoy doing the math more. So the momentum of the man is equal to the mass times the velocity, and this is in the x direction. And we can plug in our information here, 61 kilograms. Multiplied by V, which in our case is 1.8 meters per second. That means the momentum of the man is going to be 110 kilogram meters per second, and that is in the x direction, the positive x direction. Because the momentum of the man and the log are balanced out initially, so they're equal but opposite initially, we know that the momentum of the log is just going to be the negative momentum of the man. Since we know that, we can just find P log, and we know they're equal but opposite, so that makes the momentum of the log negative 110 kilogram meters per second in the x hat direction. And then we can rearrange our velocity equation, solve for velocity. We can rearrange the momentum equation to solve for velocity, and plug in our information here. And the log's mass is 320 kilograms. And that will bring us to a final answer of negative 0.34 meters per second, and that is in the x direction. So always indicate your direction to me when you are finding the velocity. And it states velocity, so it wants you to give the direction. Oh, this is that pendulum problem that I mentioned during the concept video. So we will be working that now. And I will sketch that the best I can. Okay, so it says we have an object of mass m, and it's fired with an initial speed at the bob of a pendulum. That bob has some mass m and is suspended by a rod. But after the collision, the object and the end of that pendulum the bob, they stick together and they swing. They're going to gain a height h. Now they stick together, so that means this is an inelastic collision. They stick together. So before I have here's this. It has some mass m. This is the rod and the pendulum bob. And there is another mass over here moving towards the bob of this pendulum. So once they collide, we now have this mass and this mass attached together, and they are both moving until they hit some height h, and then they'll be swinging back in the other direction. So we only have variables here. We know, since this is an inelastic collision, we know two things. Number one, momentum is conserved, so P final is equal to P initial. Number two, our kinetic energy before and after is not equal. So let's think about what that means. At the end, and since the kinetic energy is not equal, let's go ahead and look at the momentums first. P final would be the mass of both of these, so m plus m, times our final velocity. And I'm going to go ahead and write that out. So it's m plus m multiplied by the final velocity. And that's equal to the initial momentum, which is the mass times the initial velocity. You'll notice here that I'm only including one term, and that's because initially only this mass is moving, and that's why I used a lowercase m here and here and not a capital M. I tried to make that obvious. Okay. Now, at the point just after the collision, we need to know what the kinetic energy is so we can later relate the kinetic and the potential energies together. Well, why would we want to do that? Because potential energy equals mass times gravity times height, and we do need to find the height. So now let's go ahead and rearrange this equation so we can show it solving for velocity, okay, the final velocity. And that would be the mass times the initial velocity of this one, divided by, I just keep writing and I don't need to, okay. There we go. That's what the final velocity would equal. We need the final velocity so that we can use that to solve for our kinetic energy. We have kinetic energy, and we know they're not the same, but it's equal to 1/2 mv final squared. Well, we just figured out what v final is. Yes, it's just with variables, but we still know. So let's plug in what we know, and be careful here so you don't accidentally miss a variable. M, okay. Oh, I am so sorry. I have already made a mistake here. For the mass, again, after they're both moving, when we actually have a final velocity, we have both of the masses together. And then we can plug in this information. And then we can simplify this, and it will simplify to the following. K equals 1/2 mv, and we're going to square the whole thing, not just the mass and not just the velocity, divided by m, the little m, plus the capital M. Now, since the kinetic energy at the end does not equal the kinetic energy at the beginning, that means some of our kinetic energy was actually converted into potential energy. And that potential energy will let us figure out how high the m plus m traveled. Okay, so we're going to say that the kinetic energy is equal to the potential energy. And let's go ahead and replace both of these. So we have 1/2 mv, and we're squaring that, over m plus m equals, again, we have both masses. Make sure you put both of them times the gravity times the height. Now we have to rearrange this so that we're able to solve for h. Okay, and I'm going to go through this part with you because this part is slightly confusing, or it can be. It's really easy to lose track of variables because we can't simplify them as easily as we can with actual numbers. Okay, so let's do that. The first thing I'll do, we obviously want to get h by itself. And when we do that, we're going to see h equals 1 divided by 2g. Okay, so I moved the g over here. And I end up with something that looks like this. That is the same thing. So it's okay if you want to write it like this. Or if you prefer to put everything together and write it like this. So this is me writing the same thing in 3 different ways. All right. And when I divided this, so I divided both sides by the m plus m, and I moved it over here. That's how we ended up with this squared term. And that is what h equals. So again, I don't care which of those 3 ways you write it. All 3 are correct. They're all 3 saying the same thing. Now in this problem, we are in outer space and we have 2 astronauts who are throwing parts of their lunches. And they're throwing it because they're going to trade them. So they're trading them, I'm sorry. One of them has an apple and one of them has an orange. The first astronaut, so here is our astronaut. Oh boy. There's our first astronaut. And here is our second astronaut over here. You literally cannot tell this is an astronaut. Okay? But y'all know what I'm going for here. Okay, it says that the first astronaut is going to throw, and I'll do this in a different color. He's going to throw something towards astronaut 2. So here's number 1, here's number 2. This one is tossing. I'm going to draw a dotted line to represent the axis that they're tossing. Let's set that as the positive x direction. That makes a lot of sense. This will be the y direction. So this first one is tossing the apple, and it's going to travel in this direction. And this astronaut 2 is tossing an orange in this direction. The 2 fruits end up hitting each other in the middle, and then they move in different directions. So this is an elastic collision. They have collided, but they are no longer touching. So they have moved away from each other. When they moved, so one of them is moving off over here. That's the apple. And the orange is moving off in this direction. Okay, so there's our orange. We were told the angle that the orange moved off with, 42.0 degrees. And we were told the final velocity, which is 1.16 meters per second. We were not given any final information for the apple. So we are going to need to find it. We want to find the final speed and the direction of that apple. Okay. Well, since this is an elastic collision, we know 2 things. Number 1, the final and initial kinetic energies are the same, and the final and initial momentums are the same. Since this is unique to elastic collisions, that is what I'm going to use to help me solve this problem. Okay, so my initial kinetic energy is just going to be the sum of the kinetic energies of both fruits. So here is the mass times the velocity of, we'll say, the apple squared plus the mass times the velocity of the orange. Ooh, that's really hard to read. Okay, so this is for the orange, this is for the apple. I hope y'all are able to see that. Okay, let's plug in the information that we know initially, and we know all the information initially. So we see the speeds and the masses of everything initially, which is great. That's going to make this really easy to solve. So let's plug everything in. That's 0.130. This is 1.11 plus 1/2. 0.160 and 1.21 squared. That makes our initial kinetic energy 0.197 joules. Now we need to do the same thing for the final kinetic energy. However, we don't have everything we need. We have almost everything we need, and this is actually fairly easy to solve. So it's the same situation. We're going to do this again, but this time we're only looking at the final velocities, so we can plug in what we know, which is that 1/2, and this is for the apple, this is for the orange. We know the mass of the apple still is 0.130. We do not know the final velocity. Plus, we know both the mass and the final velocity for the orange. Oops, that's not 1.16. What am I doing? Oh, wait, yes, it is. I'm sorry. That's squared. So I see here that my final kinetic energy is equal to 0.065 VF plus 0.108 joules. Oh, VF squared. Sorry, I forgot that part. Okay. Now, we know, because this is an elastic problem, and I have to erase more again. I hate having to erase all of this stuff. Since we know this to be true, we know that the initial and the final kinetic energies are the same. Let's replace the final kinetic energy with the initial energy, which is 0.197 joules, and that's equal to 0.065 final velocity squared plus 0.108 joules. Once you do this math, you should find the final velocity is 1.17 meters per second. So now we just need to figure out what theta is. To do that, we are going to need to use the fact that momentum before and after is equal. All right, we can choose to do this a couple of ways. So let me erase all of this, and I'm going to go ahead and erase the final velocity as well. Hopefully you wrote that down. You can pause it and go back. It doesn't matter. Okay. So if P final and P initial are equal, this is also true. 0 is equal to P final minus P initial. I just rearranged that. This is moving at a clear angle. So we can look at either the X or the Y direction. It doesn't matter. But I'm going to choose the Y direction so I can use this angle right here as it's given to me. If I want to use the X direction, I would have to subtract that from 90. Please make sure your calculator is in degrees and not radians. Mine was in radians for a while. And I couldn't figure out why I kept getting a very strange answer until I realized I was in the wrong setting. So now we're thinking back to what we've been doing for many units before, where we have to look at the sine or the cosine Okay, here is what we have. We already found what this was equal to, so we know what this vector is. And we're going to end up using or replacing the momentums. So 0 equals m1v of the first fruit, or the apple. Or you can say the orange, it doesn't matter. I'll make that, it doesn't matter. Orange, apple, we're about to look at both of them. And we're going to multiply that by the sine of theta, okay, minus the mass times the velocity of the second one, whichever you choose that to be, multiplied by the sine of 42 degrees. Okay, now we need to rearrange this so that we can actually solve for theta. So let's get the sine of theta over by itself, plug all this other information in, 0.160 multiplied by 1.16 multiplied by the sine of 42 degrees. Okay, there's this first part, and that is divided by 0.130 multiplied by 1.17 meters per second. You're going to end up getting the inverse sine of 0.0817, and that should give you a final answer of 54.8 degrees. So that would be our angle that the fruit moves off at, that the apple moves off at. So that one was slightly more challenging just because we had to find this angle, and it's because it's in 2 dimensions instead of just 1. Those one-dimensional problems are a lot easier. That brings us towards the end. We're going to look at a center of mass problem. And I've included this diagram because there's a lot of information given to you in the problem. We see that the upper arm is vertical, okay, and we set our coordinate system to make the most sense. And the lower arm and the hand are both horizontal. Okay, so the hand and the lower arm are going to be in the X direction, and the upper arm is in the Y direction. We want to find the center of mass of the arm in this particular configuration, knowing the following information. We know the mass and the center of mass for the upper arm, the mass and the center of mass for the lower arm, and then the mass and the center of mass for the hand. So all of that is labeled for you. Okay, if you take a look at your formulas that you have, I hope you found this one. So we're going to find the point for the center of mass. We have 3 different sections. We have the upper arm, the lower arm, and the hand. So I'm going to have to add this part 3 times. So that's going to be equal to the mass times the position of the upper arm plus the mass times the position of the lower arm plus the mass times the position of the hand. This is all happening for the X direction. The X. So this term right here for the upper arm, let's just get rid of it because the upper arm has no X direction, only a Y direction. So let's just plug in the rest of the information. So that's 0 plus the mass of the lower arm is 1.6 and the center of mass is 0.12 plus 0.64 and that center of mass is 0.4. Then we're going to divide all of that. Oh, I didn't even finish writing this. So it's mass of the upper arm plus the mass of the lower arm plus the mass of the hand. And here we're going to have 1.6 plus 0.64 plus, and we do need to factor in the mass of the upper arm. It will not disappear. 2.50. So for the X point, you'll find that the center of mass is 0.095 meters. We need to do the same thing for the Y components. So go ahead, pause the video and try that now. All right, for the Y components, we have the center of mass for Y. You're doing the exact same thing, but this time the hand and the lower arm have no values in the y direction. So they're both going to go to 0. So this is going to be a little bit easier. So let's just factor in the mass and the position for the upper arm, which is 2.5, and that's multiplied by 0.18. That is going to be our center of mass. And you're still going to divide that by the mass of all three parts together. So again, 2.5 plus 1.6 plus 0.64. And you should find that in the y direction, the point is also 0.095 meters. And if we plotted that on a graph, we would find our point is 0.095, 0.095. So that's the x and the y component for that point. Now for part B, and y'all should try this one on your own before you watch me do it. Oh, I think I actually put it on a different slide because, yeah, I did. I think I put it on the next slide. Okay, let me pull that up now. Okay, so for part B, we now have a baseball placed on the palm of this person's hand. We know the radius of the ball, so we want to find the center of mass of this system. Well, I'm sorry, the system with the ball included. So it would be the whole system. I should not have just drawn, it'd be the whole system. But now we have a ball in this person's hand. Okay, let's go ahead and add all of the masses in the arm because we're looking at the arm as one whole system. We're not looking at the individual components of the arm. So the mass of our arm is equal to 4.70 kilograms. We're going to do the same thing that we did last time, and I hope y'all figured this out. You're going to find the x and the y components. So for the x component, for our center of mass in the x direction, we know the arm is 4.70 kilograms. And our point, well, we found that in the previous part, in part A, it's 0.095. Plus, I ran out of room over there, the mass of that baseball times its position. Sorry, I just lost my thought process. Okay. And then you're dividing all of this by those two masses added together, which is 4.70 plus 0.14. So in the x direction, or that x component, is 0.10 meters. Now, we're doing the same thing here. And if you're wondering where this 0.4 came from, it's because we're looking in the x direction. So we're looking along this axis. And from here at the origin to here, which is where our baseball is, it's 0.4 meters. And in the y direction, so y center of mass, okay, we have 4.70. Again, you found this position in the previous part, and it was also 0.095 plus 0.14. And then to find the y position, well, we see it right here. It's this far away from the hand, 0.037 divided by 4.70 plus 0.14. Do that math, you'll find 0.093 is that position. So if I wanted to plot this, it would look like so. Okay, so that's my x direction, that's my y direction, my x and y component. Okay, that's the center of mass problem. And finally, let's look at a problem involving thrust. So we're looking at the lunar lander, and we are told that it produced this much thrust. So this was the force that it had at liftoff. We see the rate at which the fuel was burned, and now we want to know the speed of that ejected fuel. So again, take a look at your equations, and you should find the one that tells us that thrust is equal to the change in our mass divided by the change in time multiplied by the velocity. All we have to do here is plug in our values and solve. Okay. You might be saying, oh, well, we weren't given time. Sure we were. We were told that 6.40 kilograms per 1 second is burned off. So we know that's our change. So the thrust here, thrust equals 6.40 divided by 1 second. Oh, I'm sorry, we have thrust. Why didn't I write that in? 15,600 newtons equals 6.40 kilograms per 1 second. And that is multiplied by the velocity. We solve for velocity and we'll find 2,440 meters per second is the final speed. So that is how you would do your thrust problem. And that brings us to the end here. If you have questions, please reach out to me. Otherwise, I will be back next week with the next chapter, chapter 10. Y'all have a good day.